Hello, my name is Daniel Lee, and I am a professor at the Simon Fraser University. We are located in Metro Vancouver area in British Columbia, Canada. Today, I'm going to talk about a new paradigm for designing a wireless medium access control protocol. We named this as the neighborhood map based approach because we use what is called the neighborhood map. Here is the outline. I will first try to motivate this new approach. Then I'll spend some time explaining important features of this new approach. And then I will show some analysis, namely, I will show how this new paradigm can also solve the hidden node problem. And then I'll conclude my talk. Energy efficiency is extremely important for the wireless sensor network for longevity of its operation. Energy can be typically saved by nodes going into the sleep mode during inactive periods. But the difficulty is that inactive periods may not be predetermined in most applications. And while in sleep mode, a node cannot receive data and it may miss some incoming data. So the motivation for exploring new approaches for us is to uh, design a medium access control protocol uh, with an attempt to minimize the duty cycle uh, without missing data reception uh, in the face of uncertain inactive periods. We want to facilitate lowering the duty cycle. If you knew in advance all data traffic during the network operation, hypothetically, we can optimally schedule the transmission and reception of all data packets of all nodes to minimize the duty cycle. But in many applications, the data traffic is not predetermined. Even if the data traffic were deterministic, um, the packet scheduling would be too complex a math problem if the number of nodes is large and the duration of the network operation is long. So our idea is what we call distributed packet reservation. That is, nodes negotiate with their neighboring nodes and schedule their transmission and reception of packets so that packet collision is avoided and duty cycle is low. Now I'll present a few important features of this paradigm of distributed packet reservation. First, for nodes to schedule packet transmission and reception with one another, they'd better agree on time. So we make the nodes synchronize their time frame. So in this approach, time frames must be synchronized. We define what is called a superframe. A superframe consists of a predetermined number of time slots. So the time axis can be basically thought of as successive superframes during the network operation. Packet scheduling means deciding which time slot of the superframe will be used for which node's transmission and which node's reception. And all nodes can synchronize the superframe structure by each node transmitting its own beacon packets or beacon messages. Then nodes can synchronize to the coordinator node. Perhaps the most important feature of this new paradigm is distributed and local scheduling of packet transmission and reception. If node A is to send a packet to node B, these two nodes should agree on which time slot or time slots will be used for A's transmission and B's reception. Such an agreement can be achieved by exchanging control packets. For example, if node A wants to send a data packet to node B, node A can send a control packet called request. The request type control packet. It basically is saying to node B, I'd like to send a data packet to you, and I propose to transmit in the 7th time slot of the superframe, because that slot is available where I am. Then node B receives this request message, and it can reply with acceptance or deny. If the 7th time slot is available in the radio range of node B can say, okay, I can receive at that time slot, so transmit at that time slot. So that way packet transmission and reception can be scheduled. Now then, one question is which time slots will be used for exchanging these control messages. For now, we can assume that each node has its own control time slot when it can receive a control packet. But that is for simplicity of our discussion. In fact, even control time slots can be scheduled. Anyway, so one requirement in scheduling is to avoid packet collision. And in the next slide, we'll discuss how this packet collision can be avoided. To avoid packet collision in scheduling, the scheduling nodes must know the schedules of the neighboring nodes. So each node, say node N, each node maintains the list of neighboring nodes and what we call the neighborhood map. The list of neighboring nodes is simply the list of nodes within the radio range of node N, and the neighborhood map is just a summary of schedules of node N's neighboring nodes. The neighborhood map can be implemented in a data structure like an array. So if you use an array, array elements correspond to the time slots of the superframe. So if there are 1,000 time slots in a superframe, then the array of the neighborhood map will have 1,000 elements, and the value of each element indicates the schedules of the neighboring nodes. Let us discuss some details about the neighborhood map values. So we denote the neighborhood map maintained by node N as capital M sub N. So the subscript N refers to the node that maintains this neighborhood map. The array elements Fi refers to the superframe sequence number and the time slot number. So F is the superframe sequence number, I is the time slot number. So let's focus on I. This time slot I is associated with the time slot of the superframe. So the value of the neighborhood map at time slot I indicates the scheduling status of time slot I, the ith time slot of the superframe. So if this value is 3, that indicates time slot I is scheduled for node N to transmit a data packet. If this value is 2, that indicates that time slot I is scheduled for node N to receive a data packet. If this value is 1, that indicates that time slot I is scheduled for node within a radio range of node N to transmit a data and that node N ought not transmit or receive a data packet during time slot I. So node N is not doing anything, but a node within the radio range of node N is either transmitting or receiving. Because of that, node N should not transmit or receive because that could cause a packet collision. The indicator value 0 indicates that no node within the radio range of node N has been scheduled during time slot I. So time slot is free. Let's take an example of the neighborhood map values. So we consider this example of 5 nodes, nodes named A, B, C, D, F. And let's say node A is scheduled to transmit a packet intended to node C. So let's say in time slot I of the F superframe, node A is scheduled to transmit a packet to node C. So A is transmitting and C is receiving. And let's say no other node is transmitting or receiving in time slot I. Then the indicator value of a neighborhood map maintained by node C is 2 because node C is scheduled to receive. Then the neighborhood map maintained by node A has value 3 at time slot I because at time slot I, node A is transmitting. Let's take a look at the neighborhood map value of node B. Node B is not doing anything, but node A is within the radio range of node B. So as far as B is concerned, its neighbor is transmitting. So the proper indicator value, the correct indicator value should be 1. So if node D sends a request message to node B proposing to transmit a packet at time slot I to node B, then what should node B do? Node B should deny the request because node B knows that node A is transmitting at the ith time slot. If node D were to transmit during the ith time slot, both node A and node B would be transmitting in the same time slot, namely the time slot I. Then those two transmissions will conflict When I have conflicts at node B's reception, there'll be packet collision at node B between a packet transmitted by A and a packet transmitted by D. So when the indicator value is 1, if a node receives a transmission request, then it should deny the request. As seen in the example of the previous slide, the indicator values in the neighborhood map guide and restrict scheduling. I'd like to note at this point that the neighborhood map values and the list of neighbors are shared between neighboring nodes. So the neighborhood map and the list of neighbors are included in the beacon messages that every node transmits periodically once per superframe. And this beacon message contains this neighborhood map and list of neighbors. Also, I'd like to remind you that beacon messages are also used for synchronization, as I mentioned earlier. As a node acquires new knowledge about the schedules of other nodes within the neighborhood, the node must, of course, update its neighborhood map. If a node, say node N, takes a new action, like if node N agrees to receive a data packet in ith time slot in the fth frame, then indicator of ith time slot at the fth time frame should be updated to 2. So if node N, say, receives a request message from its neighbor and newly agrees to receive a data packet in time slot 7, for example, then the neighborhood map value, the indicator value at time slot 7 should be updated to 2 in accordance with the definition of these indicator values presented earlier. Also, if a node receives a neighborhood map value of its neighboring node, then that gives new awareness of what's going on in the neighborhood. So node N must also update its own neighborhood map value. Let's consider an example of neighborhood map update. So again, in this example of 5 nodes, where A is scheduled to transmit to C. Node A is scheduled to transmit to node C at the ith time slot of the superframe. Well, initially all nodes indicator values are initialized to 0. When this transmission is scheduled, let's say at some point node C and node A are aware of its schedule, so the indicator value of the neighborhood map maintained by node A is 3, and that maintained by node C is value 2 at the ith time slot. And suppose these two values were updated but nothing else. So all the indicator values at time slot I for node B, D, F are 0. Now then, every node transmits its beacon periodically. So node A transmits its beacon, and its beacon contains node A's neighborhood map. Then node B, which is within the radio range of node A, will receive node A's beacon. So node B will become aware of the neighborhood map values maintained by node A. And so node B finds out that time slot I has indicator value 3 in node A's neighborhood map. So then node B will find out at that point that node A is scheduled to transmit during time slot I. So node B realizes at that point that its neighbor, namely node A, is scheduled to transmit at time slot I. So then node B must update its own neighborhood map value at time slot I to the value 1, because node B realizes that its neighbor is transmitting in time slot I. Well, node C also receives node A's beacon and therefore node A's neighborhood map. And node A has indicator value 3 at time slot I. So as far as node C is concerned, its neighbor, node A, is transmitting at time slot I. But C happens to be the receiver at time slot I of the packet transmitted by node A. So C knows already that C is indeed the receiver of node A's transmission. So the neighborhood map value of C remains 2. Node C does not update the value to value 1. The update rule for the indicator values can be constructed based on the meaning of the indicator values. So this slide presents the neighborhood map update rule. The leftmost column has possible indicator values of node A, and this is for node A to receive node B's neighborhood map contained in the beacon. The top row has possible indicator values of node B's neighborhood map that is received by node A. Then the cells in the bottom 4 rows and right 4 columns are the updated value of the indicator based on the meaning of the indicator values. We note here that sometimes a node can see very unexpected neighborhood map values from its neighbor, and it may not make sense, and in those cases the conclusion is that some of the neighborhood map values are incorrect. In other words, the node's perception of the current scheduling is not correct. So that indicates some incorrectness of their perception. What do you do with that? Well, there are two things we could do. We could design additional mechanisms to correct the perception or correct the neighborhood values. Or we could just leave it alone. Then because the beacon transmissions are periodic, eventually the incorrect perception will be corrected. I just finished presenting to you three important features of this new protocol, or rather a paradigm for designing a medium access control protocol. Now let us have some analysis of it. So I'd like to show you that with the scheduling approach, we can avoid the hidden node problem of wireless networks. So what is the hidden node problem? Let's see. The usual carrier sensing multiple access protocol has this hidden node problem. This slide illustrates that problem. So again, let's take the example of 5 nodes. And let's say C is transmitting to A, and so C's transmission can be heard by A because A is within the radio range of C, but node B cannot hear it because node B is out of the radio range of node C. So as far as B is concerned, B does not know C is transmitting. So according to CSMA protocol, B can transmit. But then A can hear both C and B, so there is a packet collision at node A. And this phenomenon is called the hidden node problem. Let's take the example of 5 nodes with our protocol. So suppose node C wants to transmit a packet to node A, then it sends a request message to A, and node A agrees to it. And let's assume that they've scheduled this transmission in time slot I. So then the neighborhood map of node C, the transmitter, has indicator value 3 at time slot I, and node A has indicator value 2, and beacons are transmitted from all nodes, and these beacons have neighborhood map values, and node B, upon receiving the neighborhood map values of A, will update its neighborhood map value also. So basically at time slot I, node B's indicator value will be 1. So with that, then B will never transmit in slot I. B will never transmit in time slot I because node B's indicator value in its neighborhood map in time slot I is 1. And according to the rule of this protocol, B or any node cannot transmit in time slot with indicator value 1 in its neighborhood. I've shown you how these indicator values and neighborhood map can avoid the hidden node problem. And in doing so, I implicitly assume that the channels are symmetric. So what happens if the channel or channels are not symmetric? It turns out that the protocol still works, even if the channels are asymmetric. And the details of that is in the paper. So I will defer that discussion to the paper. In this talk, I presented a new paradigm for designing wireless medium access control, which is based on local reservation and the neighborhood map. Uh, I showed that this approach solves the hidden node problem. Now I also want to note that this approach allows for spatial reuse of the channel. That is, nodes far from each other can transmit at the same time without causing interference or packet collision.